Let's talk about methane a little bit. We're trying to develop some new programs in methane, and we're trying to develop a new methane center at the Institute for Secure and Sustainable Environments, which I now direct. The good about methane is that U.S. is expected to achieve energy independence in 2016. It did achieve it, and should surpass Saudi Arabia as the top producer of oil by 2020. These changes have been largely due to shale fracking for oil and gas. We've seen rapid decrease in the price of oil and gasoline at the pump, and in the last few months reaching some 5-year lows. This in turn has stimulated the economy. Per the President's State of the Union address in 2012, shale gas and oil reserves in the U.S. will last for over 100 years. Combustion of methane produces about half of the amount of CO2 relative to coal, and a third as much as oil, reducing overall CO2 emissions too. Methane has other environmental benefits, including less what we call SOx and NOx, and volatile organic carbon emissions produced during combustion relative to other forms of carbon. Methane can also be a cheap feedstock for valuable products, including remediation of other toxic compounds. So in this schematic, you can see conventional, and we term all fracking as being non-conventional oil and gas recovery. But going down into these sandstones, through these sandstones into this gas-rich shale is basically what fracking is all about. And of course, we also can get methane from coal beds. We can get methane from conventional gas sources in sandstones and in tight sand gases and in tar sands like we have in Calgary. And I was just up there last week, and they have a serious problem that they create a lot of waste using superheated water to inject underground to solubilize the oil and bring it to the surface. But then they have this gigantic amount of water that's toxic that they have to take care of. So hydraulic fracturing is basically taking water, large amounts of water, mixing it with some chemicals. And they do this because it might help solubilize things and also reduce the amount of bacteria that are in the wells and potentially clogging the wells and that sort of thing, and clogging the pore structure. So by injecting this water under high pressures, we fracture this shale, and that allows the oil and the gas to be released into the water. So we have a mixture of pressurized water, 1.8 to 8.7 million gallons of fresh water per well. Chemicals and sand is injected to help keep the pores open and to create fractures that release the gas. In just since 2007, in less than 10 years, we've seen a 700% increase in shale gas production in the U.S. We are technically energy independent now. Canada's not real happy about that, especially with the tar sands, because they've had to lay off 10,000 people up there, because we no longer buy that much oil and gas from them. So the projections are that shale gas offsets declines in other U.S. supply, and so our net imports are going down and down and down. And basically, we still do some importing, but we don't have to. Shale gas has taken up the slack on this. We've got some associated onshore and associated offshore production of gas, tight gas, coal bed methane, and associated with oil. There's a lot of battle of forecasts, okay? And, but most of them show that shale gas has driven U.S. production to record levels, and it will continue probably for at least the next 20 or 30 years. before it slacks off. Now, on the good side too, I actually have patents on methane for bioremediation. So methane will encourage methane oxidizing bacteria to grow that are naturally found in the soil. And they can degrade over 1,000 compounds fortuitously. So they have to have methane as an energy and carbon source, but the methane monooxygenase that they produce will degrade all of these other compounds that might be found in the environment. So what we do is pulse the methane with air, and it's below the lower explosive limit, so no problem of having anything going on and potentially fires and that sort of thing. So this is what we did here and this is actually real data for a model. Let me get this to work, there we go. And that was a normal sized man. We put in 2 horizontal wells, and this was in South Carolina. This is where the water table was. And so we're injecting gas into this area. These are clay lenses. And basically, you can't get these wells perfectly parallel to each other, so they're slightly askew. So you know this is real data. As we start injecting here, you'll see this is the chlorinated solvents that were disposed of at this DOE site at the Savannah River. This is the bacteria, the methanotropes, actually growing. And you can see them grow through this clay where a lot of the chlorinated solvents have been trapped, and it's disappearing. And in fact, here you see I've overlaid chloride concentrations. So it's being degraded completely, the trichloroethylene, to CO2 and chloride. And so it's complete degradation. It happens very fast. So we can clean up these fields very, very fast. So in fact, I have done that at a number of different sites, including Poland. And this is another one at the Savannah River site. It was an oil seepage basin. And basically it had lots of methylene chloride, vinyl chloride, and that sort of thing. We were doing, looking at a record of decision, and the preliminary work that we did to demonstrate this by just trenching in 2 horizontal wells, using a catfish pond aeration pump, and then injecting methane from a tanker truck. And the blower could generate about 200 standard cubic feet per minute. We basically would put in methane, nitrous oxide as a nitrogen source, triethyl phosphate as a phosphate source. So carbon, nitrogen, phosphorus. And so when we did that, we had completely cleaned up in less than 6 months. So everything was below detectable limits or way below what the EPA required. And so a no action rod was then approved right after that, just from this demonstration of that technology. We've also done some work on landfills. Of course, we know that landfills can generate a lot of methane. It's required to capture methane as much as you can. Some people try to use it, but it's a little bit difficult. Methane is 9.9% of all greenhouse gas emissions. Landfills are the largest anthropogenic source of methane. Less than 26% of all methane from landfills is trapped or used. So there's a big problem there. So we went and set up some of these catfish pond aeration pumps into the leachate collection system. So the normal way you set up a landfill is to put in a liner, put in a gravel bed and a leachate collection system, put in the sanitary waste, and then put a cover over the top. And then any leachate that collects has to go to a sewage treatment facility, okay? And then, of course, methane traps are in this cover. Now, because it's a dry tomb technology, it does not degrade things very fast. So this is why you can see all sorts of studies that show that you can read a newspaper that's been in a landfill for 20, 30, 50 years, and you can still read it because it hasn't decomposed at all. That's not the case if you inject air and you take the leachate and recirculate it onto the sanitary waste, okay? So basically a closed system. You no longer have to collect the leachate and dispose of it, which is a significant cost. It no longer generates methane because in an aerobic environment you can't inject methane or can't get methane. Of course, we get a lot of degradation for any methane that's residual too. So this is at, let's see, this was the Richmond County landfill in near Augusta, Georgia. And this is where we did this full-scale demonstration. And this was in the middle of the summer, and you can see it steaming. So basically, we turned it into a giant compost pile, okay? Increased biodegradation rate 30 times. Increased subsidence 15%. In some of these landfills where we've done this, it's sunk as much as 11 feet. We've eliminated the need for leachate treatment, and that's 150,000 gallons per month. We stabilized the refuge mass in less than 2 years versus 30 or more years. And all of these liners and stuff leak almost immediately after they're put in. So this is a much better way, I think, to do this. However, the landfill operators are fairly resistant to it because EPA says you do this dry tomb technology. Even though every time we've gone to the EPA and talked to the regulators, they immediately allow this too. But the landfill operators are also afraid that you'll get an underground landfill fire. Well, that's actually impossible because you have wetter garbage and because you no longer have methane. Yes, you're injecting air, but that's increasing the degradation rate. So we see decreased long-term liability and monitoring costs, decreased leaching of metals and organic contaminants, decreased methane generation, reduced life cycle costs, so return on investment is less than 1 year. So you can recover your costs pretty rapidly. Now what we've also been trying to do is conversion science, and another governor's chair, Tom Zawazinski, is using various types of catalytic systems to convert methane to other products. And he has some grants on this, and we're trying to work together to see how we can do this in methane that we can capture from TVA dams. So because some of these TVA dams are getting pretty old, there's a lot of sediment buildup behind the dam. A lot of methane is starting to come to the surface in these dams. So that's a worry for TVA. And incidentally, TVA is switching all their coal-fired steam generating plants over to methane. As we have here, you know, we switched last year to methane from coal. Gas hydrates is also a potential problem, especially if we consider global warming, because basically if you have a low enough temperature and a high enough pressure, the methane will form a crystal surrounded by cages of water, and that's why you can see pieces of ice can actually be lit on fire. This is gas hydrates, and we see this in deep ocean margins all around. Most of it is probably biogenic methane, so it's been created by particular carbon material that's been sloughing off the land. So if you see here, there's just a tremendous amount of methane hydrates all around the world. So we're not going to run out of methane for a long time, but it's a worry that methane may actually be a problem as the world warms up. However, both in the Arctic and in the Gulf of Mexico, during Deepwater Horizon, we saw in the Gulf of Mexico that there was tremendous amounts of methane being released. Well, most of that did not get to the surface, because at 400 meters where the gas hydrates would melt, we saw tremendous increases in methanotrophic bacteria, methane oxidizing bacteria. And they basically scarfed it all up. We've seen the same thing in the Arctic, where we've done warming studies where we thought on these tundras, with all the organics that's trapped there, you'd get a whole bunch of methane production, and then you'd have a net methane flux. Well, there's not a net methane flux, because the methanotrophs rise up with a response to any methane being there, and they're basically universally found everywhere. The bad: methane is 30 times more potent as a greenhouse gas than carbon dioxide. Methane has emerged as the keystone greenhouse gas of the 21st century. Recent Intergovernmental Panel on Climate Change suggests that greenhouse gas emissions must be substantially curbed over the next 35 years, with overall fuel switching from coal to gas and greater reliance on nuclear and renewable energy sources. The US EPA predicts methane emissions from oil and gas activities are predicted to grow at least 4.5% over the next few years. Methane is explosive and toxic. According to the US Geological Survey, more than 50% of people in the US use groundwater for drinking, sanitation, and other household uses, making groundwater an important resource to protect. And there's a lot of controversy about this with fracking too. As I said, Deepwater Horizon, there was tremendous amounts of gas and oil being released. And you can go and see a bunch of the papers that we've done on this already. And so, could warming increase melting of gas hydrates in oceans and tundra? Now, my hypothesis is that the Gulf of Mexico is cleaner than it should be. That sounds bizarre, but because of all the episodic releases of methane from natural seeps, 400,000 to 1 million barrels of oil and gas a year, tremendous amount of organic degrading capacity by the methanotrophs that are there. And in fact, things are lower than what we expect from all of the inputs from the Mississippi River and from Louisiana coast and the amount of organics that are going in. So we actually looked at the catastrophic release, and we could show that there was a DO anomaly, and this is from Kessler and Valentine's paper. We also showed that there was a isotopic signature change, and it didn't happen until the well was capped, so all the good stuff was eaten, and then they started degrading the methane, okay, which takes a little bit more energy. But they were degrading at 84% microbial oxidation of the methane after just 2 weeks from the well being capped. Fracking effects on drinking water. We've all seen these things. These are some figures that we find from and some studies that we've been doing in Pennsylvania. And you can go to our website and see this. We're looking at streams where the fracking fluid is dumped. And these are just basically to show some differences in impacted streams and non-impacted streams, and the differences in microbial community structure and things like this. And of course, these are sort of famous, but this has gotten the public all upset about fracking. But fracking, you have to remember, is, and it's in all of the scientific literature too, but fracking is from formations that are at least 6,000 or 7,000 feet deep. You never drill a drinking well down that far. Plus, there were aquicludes at various levels above these shale formations, and that would prevent any methane from coming up into potable water. So the only possibility for contamination is usually improper drilling, okay? So leaking from the drilling or re-injection of the flowback fluid, which does happen too. So we're trying to do things that where we might decrease the amount of flowback fluid and decrease the amount of these biocides that they're putting in the flowback fluid and things like this. So there was a study that got quite a bit of attention in ES&T, and basically it said that fracking operations in Ohio posed a great risk to humans in terms of cancer risk and that sort of thing. However, just recently that person needed to retract that paper because she had done a slight miscalculation. She was off by 2 orders of magnitude on the concentrations, okay? Now, I hope that doesn't affect her career too much because she found the problem herself and wrote to the journal and got it retracted. But, and again, corrected that in fact, airborne PAHs near fracking operations in Ohio do not pose an elevated cancer risk. So, you know, papers come out like this, and if you don't use some scrutiny, you might find stuff that's not quite correct that needs to be corrected. One of my PhD students in the Bredesen Center, Maria Fernandez Campo-Ayala, has also been working with me with one of my undergraduates, Sheridan Brewer. And we've been looking at in southern Pennsylvania and looking at different sites that are affected by hydraulic fracturing, different rivers and creeks. And then you can see here the temperatures and that sort of thing. We see lower pHs in these streams. We also see some dissolved solids are about the same, but the salinity can be a little bit higher than normal. So probably the most important thing is the pH. But what we're also looking at is because glutaraldehyde is one of the antibiotics that they put in there. In fact, when that's injected down well and then is in, we have bacteria that have been exposed to it for quite a period of time. What do you know? They become antibiotic resistant, and what we call multiple antibiotic resistance. So even though they haven't been exposed to anthropogenic antibiotics, because they are able to degrade recalcitrant compounds, and they can pass these genes on by horizontal gene transfer, we're seeing some increase in antibiotic resistance. So that is happening in the streams itself, okay? That suggests that there could be problems of antibiotic resistance in any of those streams for anybody that might be using those streams in Pennsylvania and Appalachia and that sort of thing. So you can see here, the biocides and other hydraulic fracturing chemicals in the stored water, and then we have the potential for environmental release of methane and some of these things into the watershed. It's usually from the well or from the disposal well, and almost never from the shale rock. And then we can also have that release into the rivers and that sort of thing that are nearby. So we're working on that right now. Now, methane is a greenhouse gas, 30 times more potent than CO2 on a mole basis, short environmental half-life, 10 to 12 years compared to 1,000 years for CO2. Atmospheric increase in concentration at a greater rate than CO2. Multiple natural biogenic and abiogenic sources contribute to 60% of the load, with 40% contributed by anthropogenic sources. So you can see here all the potential effects that climate change might have: more droughts, more wildfires, higher temperatures, damaged corals, warmer oceans, rising sea level, thawing permafrost, and so on. And of course, you can see all this in the scientific literature too. It's a hot topic. Now, according to the World Meteorological Organization, looking at the global abundance in 2013, methane is by far higher than anything like CO2 or nitrous oxide. Relative abundance is higher. The absolute increase has been higher. The relative increase is a little bit lower compared to CO2. The mean annual absolute increase during the last 10 years has been quite high, 3.8 parts per billion per year. So we're expecting to see more global carbon emissions from fossil fuel combustion and cement manufacturing. And these are million metric tons of carbon. So the ugly part also is the aging infrastructure in cities of oil and gas production and distribution lines. Facilities and they're a major source of fugitive methane emissions, and it is increasing dramatically with more reliance on cheap natural gas. The public in places has become furious about the fracking activities in some cities, counties, and some states and counties and cities have banned fracking. New York has a sort of total ban on fracking, even though it has the potential to have lots of fracking sites. Geopolitical bargaining chip in economics and foreign policy too. Now, this is a survey that was done in Boston by basically having, I think they had both planes and they had cars driving around neighborhoods taking methane concentrations. And you can see with this decaying infrastructure, we've got some serious problems. And there's more of this methane in some of these spots than we ever expected to find. So we're doing surveys on that. But at Oak Ridge, Panos Datsakas has, in the Nanosystems and Structures group, has a drone system, octocopters, that we put a laser on and a spectrophotometer on the other one, and we can go in circles and get very, very accurate and basically program these drones to go over different sites and do this. So this is in the process of being implemented right now at some sites, and we're going to do a lot more research on this. So,
what altitude?
Excuse me?
What altitude is the drone flying?
So we can go up to, the typical one can go even over 1,000 feet. Of course, now they have to be registered, okay? And I have one myself. And it'll carry a load of 10 or 15 pounds even, most of them. And they're only about, the most expensive ones are about $10,000. So we also have a lot of concern about cow, and there's actually been some recent legislation to regulate somehow cow methane. This has got to be photoshopped, okay? But, and this was actually a farmer that was trying to trap methane from his cows, okay? But anyway, what we're trying to do, and we're seeing some of this, and we've gotten some research here in the agricultural station where we have feed that produces less methane in the cows. So that's actually a potential way to handle some of that. Again, a lot of different project, and it's almost every other month I see one of these things on the gas boom and that sort of thing. Oil companies and natural gas drillers say, well, it's half clean, okay? But that doesn't satisfy the public. Charles Sims, a faculty fellow in the Baker Center in Public Policy, is also working with us on translational science in economics and policy and looking at how we might be able to control policy and look at producing wells, storage, import-export, gas mains, infrastructure development, and a variety of things like this. So we're trying to develop a whole team to do some things like this. We also want to do outreach. And so we're trying to do this with various types of systems that we would develop, and also some of the existing ones where we have See It Live and we have different types of groups going out into the field and learning about this and learning about where methane comes from and that sort of thing. And hopefully they don't see a cow like this. So summary. Methane is a major global energy resource, plentiful and sustainable. Methane represents a dominant flux in carbon cycling. Methane is a major greenhouse gas, climate change. Methane serves as a primary feedstock for chemical synthesis. Methane is an emerging market driver in energy production and conversion. Methane is a proposed progenitor substance for primordial life, astrobiology marker. In fact, I found it in the single organism ecosystem in a project that I published in Science in 2008, I think it was, for NASA. We found it 8,000 feet in the gold mines of South Africa, a single organism ecosystem. And it was a sulfate reducer that was also taking up hydrogen and using methane. Great mechanistic and quantitative uncertainty of methane sources, sinks, exists. We need to do environmental controls and rates, production and release from thermogenic and biogenic sources, rates of methanotrophic consumption in oxic and anoxic environments, because we can get methanotrophic consumption in even anoxic environments, effects of methane energy economy, environmental change in methane fluxes. What will be the environmental impacts of a strategic switch to methane energy economy? And we're in the midst of that right now. What are the social, economic, political implications? Is methane a bridge fuel to a more sustainable future planet, or is methane the solution? On what basis should we make these decisions? I have to acknowledge the fact that ICE supports this, also the Bredesen Center, and I have DOE support for a lot of different projects, and NSF and EPA. These are my students and postdocs and research associates and visiting professors. And this is one of our ex-postdocs who was with me at Berkeley, and she's now a professor at Juniata College. So we're working with her, and she gets us all sorts of samples to use from Pennsylvania. And then also we're doing some chemical analysis with Sean Capagna, and then also some people in the Loeffler lab. Thank you.
Let's all thank Dr. Husen once again.